we present VQ-SGen, a vector quantized stroke representation for creative sketch generation. Unlike traditional sketch generation, creative sketch generation aims to produce diverse, complex, and aesthetically appealing sketches, forming more imaginative depictions of familiar visual concepts, rather than generating conventional and typical representations of these concepts. Existing methods can be categorized into three types based on the representation of strokes. The first type treats a sketch as a bitmap image. This type of bitmap-based method regards pixels as atomic items, making it difficult to capture contextual information. As a result, it often generates cluttered and thicker strokes. The other two types of approaches treat strokes as sequences of points or as parametric curves. These methods typically use diffusion models to predict changes in nodes and parameters. However, they often produce non-smooth strokes. In this work, we adopt a stroke image sequence as the representation of strokes, where each stroke is represented by its bitmap image in the sequence. This approach enables better capture of the structure, position, and contextual information of a sketch. Using stroke image sequences as the representation of strokes has been shown to be effective in other tasks, such as sketch segmentation. Next, we introduce our proposed method, which mainly consists of two parts. The first part focuses on obtaining the representation embedding of the sketch, while the second part leverages these embeddings for generation. In the first stage, the embedding of strokes should be representative, compact, less redundant, and semantic aware. A discretized representation using vector quantization can satisfy these characteristics. Vector quantization, VQ, is a data compression and dimensionality reduction technique that represents a large set of input vectors with a smaller set of codebook vectors, essentially clustering similar vectors and assigning each cluster a single representative vector. Specifically, in the first stage, we first split the input sketch into a sequence of strokes. For each stroke, we decouple the shape and location information of each stroke. Then it is processed through two distinct codebooks to obtain its vector quantized representation, which is highly compact and semantic aware. The model is trained through a reconstruction task, where the obtained vector quantized representation is processed by a corresponding decoder and then relocated together into the form of strokes. Finally, the generated stroke sequence is then merged into a complete sketch. As a result, the reconstruction results can achieve clear reconstruction of the input sketch with appropriately designed hyperparameters. To better understand the properties of the discrete space, we applied the UMAP algorithm to project the high-dimensional features of the shape codebook into 2D space and visualize its distribution. Although we did not exploit any semantic-related constraints during the codebook learning, it tends to implicitly group strokes with similar shape variations, thereby achieving stable and efficient code learning and space compression. In the second stage, we designed the gen transformer by two cascaded transformer decoders. The first label transformer predicts a stroke label each time, while the second code transformer takes as input the predicted label, generating both the stroke shape and position codes simultaneously. The model first receives a start token as input, then predicts the label of the first stroke. Next, it outputs the shape code and location code of the first stroke. These predicted three codes of the first stroke are then used as input to predict the second stroke. This process continues until the entire stroke sequence is predicted. After multiple autoregressive iterations, the gen transformer generates a sequence of stroke codes. Each stroke code is processed by its corresponding decoder and relocated, resulting in a sequence of strokes. These strokes are then merged to form the final sketch output. Now, we present the statistical comparison of segmentation results between our model and SOTA methods. The results show that we outperform other methods across the majority of metrics. The visual comparison also demonstrates the superior performer of our model. We also evaluate the performance of our method through user studies. We invited 50 participants to the test, where they were shown multiple pairs of images. Each pair consists of a sketch generated by our model and competitor. For each pair, participants were asked to answer 5 single-choice questions in the bottom of the IMG. This user study shows that our method is preferred over the competing approach. Our method can also achieve conditional generation. Given a class label, an input text, or an initial stroke, our method can produce corresponding sketches with rich variations. To conclude, we have proposed a new efficient creative sketch generation approach, which runs faster, more robust, and achieves SOTA results. In terms of technical contributions, we have proposed a vector quantized stroke representation and a stroke-level autoregressive sketch generator. More details are presented on our project page. Thanks for watching.